Hi, welcome to the video solution for Edexcel Physics. This is IAL Physics Unit 2, October 2019, second video of the series. So let's start. Question number 14. The circuit shown uh, includes a fixed resistor and a negative temperature coefficient thermistor. So we have a circuit in which we have a fixed resistor between X and Y, and the YZ we have a thermistor. A potential divider circuit can be created by making connections to a secondary circuit across the resistor XY or the thermistor YZ. As the temperature changes, the potential difference across XY and YZ both change. Such a circuit can be used to operate an air conditioning unit in a hot classroom in order to keep the classroom cool. The air conditioning unit starts operating when the potential difference in the secondary circuit exceeds a certain value. Explain how the circuit should be set up to keep the classroom cool. Your answer should include detail of how a negative temperature coefficient thermistor works in terms of particle. So you remember that thermistor, which is this component, resistance of the thermistor depends on temperature. So generally we say resistance is inversely proportional to the temperature. So if temperature is increased, resistance is decrease. And the reason of decrease in resistance is that increasing temperature causing a number of electrons in the thermistors to increase. So what does it mean? If you increase the temperature, so in the thermistor there are number of electrons or conduction electrons are increased with more energy. So high energetic particle creating more and more as you keep increasing the temperature. And increasing number of electron means more electron are passing from the thermistor. That means amount of current is increased due to large number of conduction electron. So current is increasing. That's why we say resistance is decreasing. So remember, increasing temperature causing number of electrons to increase, and they are moving with the high energy. That means electron amount of current increase. So the resistance is decreased. And now if resistance of thermistor is decreasing, so voltage across YZ, that means voltage across YZ, VZ must be decreasing because resistance decrease, so voltage decreases. But this is a series circuit, so the sum of the two voltages, that means VXY plus VYZ must be equal to the total voltage, which is voltage of the power supply. So if VYZ or thermistor voltage is decreasing, that means voltage across XY should be increased. So that VXY must be increased in order to sum of these two voltage should be the same. So what does this mean? All these things we can say that voltage across XY is basically controlled by the voltage of the YZ, or you can say the due to thermistor. That means XY is the best position to connect our secondary circuit or the circuit to control the air conditioning unit. So you need to incorporate all these points in this question, and you can write all these points like that. So resistance of thermistor depends on the temperature, of course. Temperature increasing, conduction electron increasing with the energy, so more electron are flowing, so current increase. That means resistance of thermistor has decreased, meaning the voltage is decreased of the thermistor, so voltage of across XY has increased. So that means voltage across XY is being controlled by a thermistor. So the secondary circuit should be connected across XY. Question number 2. The thermistor in the circuit is replaced with a light dependent resistors LDR and a voltmeter placed across YZ as shown. Okay, so thermistor is replaced with the LDR and the voltage across the LDR is V. The fixed resistor has the resistance of 1.2 kilo ohm. The battery has an EMF of 12 volt and the negligible internal resistance. Initially, the circuit is set up in the darkened room and the voltmeter displays a reading of 4.17 volt. When the light is shown directly onto the LDR, the voltmeter reads 2.16 volt. Calculate the change in resistance of LDR when the light is shown onto it. So the idea is we have a fixed resistance value which is 1.2 kilo ohm k ohm, and we have a EMF 12 volt is there, and of course in a darkened room we have initial voltage of the LDR. That means initial voltage of LDR, I'm calling it V1, suppose V1, which is, you can say, 4.71 volt. So clearly we can figure out the resistance R1 at this voltage using potential divider equation, because we have a voltage V1, we have a R2, I'm calling this R2, and then we can figure out V2 when the circuit is in darkened room. So let's suppose V2 is the voltage across fixed resistor R2 and V1 is the voltage across LDR with the resistance R1. So my target is, I'm trying to find this R1 first from this data. What about V2? Clearly V2 would be 12 minus 4.7. So 12 minus 4.7 would be 7.29 volt. 12 minus this will give you V2. Now we have V2, so I can figure out R1. So R1 upon V1 is equal to R2 upon V2. This is the simplest equation of this a circuit in which two resistances are connected in series, basically a simplest potential divider circuit. And we can figure out this R1. So R1 would be equal to R2 V1 divided by V2. That means R2 is 1.2 into 10 to the power 3 because kilo ohm, and V1 is 4.71 divided by V2, and V2 we found is 7.29. So R1, that means initial resistance of this LDR when the circuit is in darkened room. So the resistance was 775.3 ohm. This is the resistance initially. And now what is happening when the light is shown, the voltage of the LDR changes from 2.16. So you can say that now the voltage V1 is now, I'm calling it V1 dash, suppose, new voltage, and this is 2.16 volt. And now we can find V2 dash. So V2 dash, the new voltage would be equal to 12 minus 2.16, which is equal to the 9.84. So V2 dash is 9.84 volt. Again, I can figure out the R1 dash. So when the light is shown, what is the condition? R1 dash divided by V1 dash is equal to R2, which is a fixed resistor, divided by V2 dash. So R1 dash is equal to R2 V1 dash divided by V2 dash. Clearly R2 is as same as before, 1.2 into 10 to the power 3 times V1 dash, and V1 dash in this case is 2.16 divided by V2 dash, so 9.84. So R1 dash, the resistance of LDR after light is shown, R1 dash would be 263.4 ohm. Now the change in the resistance delta R would be equal to R1 minus R1 dash. You can subtract R1 and R2. This is your R1 and this is your R1 dash. If you subtract these two, so delta R would be equal to 511.9 ohm or 512 ohm. This is the change in resistance. A student is planning an experiment to determine a value of resistivity of a metal in the form of wire by graphical method. State a physical quantities he should measure, suggesting a suitable measuring instrument for each quantity. It's all about resistivity of a wire, and if you see the formula for resistivity, so resistivity formula rho is equal to R A by L. That means you need three different quantities or three quantities in order to find the resistivity. The one is the resistance of the wire, A is the area of cross section of the wire, and L is the length. So you can say that a student is going to measure the length from meter rule, and she needs to measure the resistance from ohm meter, and then area, for area she needs to measure diameter, because for diameter is used to find the area from micrometer screw gauge. That's what you need to write all these things, and these three quantities need to be measured with these three instruments. Describe how she should use her measurement to determine an accurate value for a resistivity of the wire using a graphical method. So the idea is, if she needs to use a graphical method, that means she's going to take multiple reading of resistance and the length values, corresponding length. So you have a various reading of length and the resistance, and then you're going to plot length versus or R versus length graph. It is good because length is independent. So length on the x-axis, resistance on the y-axis, then you would have a point, and then you can plot a line of best fit. From the line of best fit you can figure out the gradient, and the gradient will be resistance upon the length. Remember, the formula of resistivity, rho is equal to resistance area upon length. So now if you see from this graph, gradient is resistance upon L. So in the formula, basically R upon L, this is the gradient. So gradient needs to be multiplied by the area. So you say that the area is going to be found from formula A is equal to pi R square. Once you have area, then gradient multiplied by area will give you resistivity using graphical method. So you incorporate all these things like table and the graph, gradient, area, and gradient times area will give you resistivity. So finally, gradient times A will be the resistivity. If you wish, you can sketch the graph in your answer. Like you can sketch something like R versus L, and then like this, and then you say gradient equal to R upon L. Question number 16. An aeolian harp is a string musical instrument that is played by the wind. An aeolian harp is shown in the photograph. So this is some kind of musical instrument. As air passes through a string, it forces them to vibrate, creating stationary waves on the strings. Explain how stationary waves are formed on the string. A typical question about stationary waves, when they ask you about production, how stationary waves are produced. So you say that two waves traveling in opposite direction. So one wave is coming from, suppose, right, from the left, the other one is coming from the right. So two waves are traveling in opposite direction, and they are interacting or interfering or superposing, whatever you wish to write. After interfering, they produce pattern of nodes and antinodes. So you say that you have pattern of nodes and antinode, and this is called stationary waves. So key points are two waves traveling in opposite direction, interfering and producing nodes and antinodes. When the string of an aeolian harp vibrate, the frequency f of the string vibration is given by the equation f is equal to ku by d, where u is the speed of moving air, d is the diameter of the string, and k is a constant. Show that constant k has no unit. So if you need to figure out the unit of k, so first you make k as a subject of the equation. So k would be equal to f d upon u. Clearly f is the frequency, and if you see the frequency, the unit of frequency is hertz, and basically hertz, this is the SI unit. You can say the base unit of hertz is S inverse. Why is that? Because frequency is basically reciprocal of the time period. That's why hertz is equal to second inverse. So f, the frequency, has a unit of second inverse, and d is the diameter, so unit is meter. S is speed, so meter second inverse. So now you can see that meter gets cancelled, S inverse get cancelled, so k has no unit. A stationary wave is produced on a string of length L as shown. Okay, length L, 3 loops. Calculate the speed of the air required to produce this stationary wave. Length of the string is 0.33 meter. This is the length. Diameter of the string is 0.15. Tension in the string is 63. Mass per unit length. Okay, mass per unit 0.58 10 to the power minus 3, and k is given. So if you need to find a speed of the air required to produce, and if you see the formula in your previous part, so the idea is the formula was given as F equal k u upon d. So this u is the speed of the air, and this u we need to figure out. So meaning, if you rearrange this equation for u, or if you make u as a subject, so u would be equal to F into d divided by k. And now if you see your data, so d is given, this is d in millimeter, and value of k is also given 0.2, but you don't have the value of frequency. That means you need to figure out frequency from the other set of values. And how do we do that? Because f is the frequency of the wave produced in the string. So we can first we're going to figure out velocity of the standing wave. So the idea is, see, this is, remember, this is our main equation that we are going to use to find u. But before u, you need to figure out first v. V is f lambda. This is velocity of the wave produced in the medium, where f is the frequency, v is the speed, and lambda is the wavelength. So for v, remember, when we have a stationary waves and it is producing due to some tension in the string, so we can use the formula v is equal to t divided by mu square root. This formula will be given in your formula sheet, or if not, you need to remember this formula. So v, the velocity of the wave or standing waves produced under some tension or force t, t by mu. So you can use this formula to figure out v. So t is given 63 Newton divided by mu. Mu is mass per unit length. This is mu. Substitute this value. So 0.58 into 10 to the power minus 3 square root. So v would be equal to 329.6 meter per second. So this is the speed, remember, but this is not the speed of the air that we need to find. This is the speed of the standing waves produced in the string. And now we have a v, this one. So we need to figure out lambda, so we can work out with the frequency, and frequency we can use here. So now lambda, now if you see the diagram, from this node till this node, this length is called, in terms of wavelength, this is lambda by 2, half of the wavelength. And how many such loops are there? So there are 3 loops. So you say that since length of the string or the wire is equal to 3 by 2 of the lambda. So this is lambda by 2, another lambda by 2. So we have 3 lambda by 2s overall, so which is equal to L. So L equal to 3 by 2 lambda. So lambda is equal to 2L divided by 3. Clearly 2L, length is 0.3. So 0.33 divided by 3, and clearly lambda is equal to 0.22 meter. So we have a wavelength. Now we can figure out frequency. So frequency would be equal to v by lambda, and we have a v here, we have a lambda here. So you can figure out frequency, which is equal to 1498.1 hertz. This is the frequency. And then use this frequency, this one, in this formula. So u would be equal to, now u would be equal to 1498.1 times d. D is the diameter, 0.15 into 10 to the power minus 3. Don't forget, this is milli. Okay, divided by k is 0.2. So u is 1.12 meter second inverse. This is the speed of wind that causing the wire to vibrate to produce standing waves. The rail of a railway track are usually made from steel, which can withstand the high stress of heavy train. However, steel can develop cracks over time, leading to accidents if not repaired. Large cracks in the rails, such as the one shown in the photograph, are easy to observe. Okay, ultrasound is commonly used to detect cracks that are too small to be seen. An ultrasound transducer transmits a pulse of ultrasound into the top of the rail and records the time taken for the pulse to return. If this time is less than the expected one or less than the time expected for the pulse to return from the bottom of the rail, a crack is present. Okay. State why an ultrasound pulse would be reflected by a crack in the air. So remember, whenever we are talking about reflection of some wave, because we are using wave ultrasound, so reflection is always occurred from the boundary of another medium. Because if wave is traveling in one medium, like this is medium 1 and medium 2, so wave cannot reflect something like from the same medium unless it reaches at the boundary of the other medium, and then it is going to reflect. And that's the idea you need to understand. So if you have a some rail, something like this, a solid one, but somewhere here you have a small crack. So if ultrasound is coming and reaching at that position, so in this gap we have air inside. That means above this crack we have a steel, one medium, and in the crack we have another medium of air. So we have a boundary. That's why the ultrasound is reflected. A data logger connected to a transducer produce a graph of ultrasound signal strength against time. Determine whether the reflected pulse is from a crack in the rail or from the bottom of the rail. Depth of the rail is 15 centimeter and speed of the ultrasound is in steel is 5,800 meter per second. So you need to figure out whether the pulse is from the crack or from the bottom. That means you need to compare time, expected time. So this is the actual depth of the rail. So we can use these data to find expected time, real time, that if there is no crack, then this time we are going to figure out. And this time will be compared on the time axis from the obtained data. If the obtained time or observed time is less than the expected one, then we say that there will be a crack. So it's all about pulse and echo question. We need to find the time. Generally, for pulse and echo question, we use equation S is equal to ut, where S is the distance traveled, use the speed of ultrasound or sound, whatever, and T is the time taken. But here the most common mistake generally students do is they don't consider the double distance traveled by pulse and then echo. You know that for pulse and echo, if this is the total distance from that point, if this is the distance between the top and the lower layer, so ultrasound is traveling, going in, covering distance S and then coming back as an echo. So total distance traveled by 2S. So don't forget to use 2S here is equal to U into T. And this T is the time which is expected for the depth of 15 centimeter. So you can say that this T would be equal to 2S. So 2 times of 15, but this is 15 centimeters, so 0.15 divided by U, and U is the speed, which is 5,800. So time, which is equal to 51.7 into 10 to the power minus 6 second, meaning the expected time is around 51.7 microsecond, or you can say 52 microsecond. This is expected time for the depth of 15 centimeter from the top to the bottom. Now we are sending transmitting pulse and the reflected pulse. So we need to figure out the time difference between the sending and the received pulse. So this is around 5 or a little more than 5, but 5 is sufficient to consider. It is not 5.02 or 5.2 is fine. And this is 30. So 30 minus 5, which is 25. So 25 microsecond. So T dash or TO, observed time, is 25 microsecond. So you say that 25 microsecond is less than the expected timing, 52 microsecond. That means there is a crack. There is a crack. So the pulse is being reflected from the crack, not from the bottom. So you just write that statement in your final conclusion. Part C, suggest why this ultrasound method may not detect multiple cracks in a piece of rail. Clearly, I told you that the wave, the pulse is reflected from the boundary of the other medium. So if you have more than one crack, like this is the rail, and one crack is there somewhere, and another crack is there, like this. So when you send the pulse, then this pulse is reflected from the top crack. So the pulse is not reaching down because most of the pulses are reflecting from the top crack. It does not reach to the bottom. So if there is a crack, there is other crack, definitely the pulse cannot reach to that track. To detect cracks, transducers are attached to the wheels of special trains. Explain why these trains must travel much more slowly than passenger trains. So you see that if the train is moving faster on the track, and here is a track, suppose this is the crack, I'm sorry, this is the crack, and this is the train which is moving. If it is moving faster, so when the train send a pulse down at the time, because there is always a delay of timing between sending and the receiving, if train is moving faster, so when the echo is coming back, or pulse is returning, at that moment, because of the fast speed, train might have changed its position. So that's what it cannot detect the exact position of the crack. So train has to move very slowly or slower than the normal one, so it can detect the received pulse from the same position. That's how you can write. Thank you very much for this video. Have a nice time.